So at this point in Chapter 6, we've gone over momentum and impulse. Now we're moving on to Part 2, which is the conservation of momentum. In situations where multiple objects collide or interact in some way, momentum is conserved. So we can take this example. We have two cars of certain mass. The cars collide in a big crash. Now this final scrambled wreckage of the car crash is going to move away with some velocity. It might be a different velocity from the initial velocity, but overall the momentum will be conserved in this whole situation. We can write this as the sum of the initial momentum, or total initial momentum, is equal to total final momentum. This simplifies down to the law of conservation of momentum, which states the total momentum of all objects interacting in a system remains constant regardless of the nature of forces between objects. So no matter what happens with objects interacting, the momentum will be conserved, unless there's external force. So this means that if the momentum of one object increases during the collision, the momentum of the other object must decrease by an equal amount to make this whole momentum of the system, we'll call that P total, stay the same. Here are some situations where momentum is conserved. First is collision, so if two cars crash, the momentum of one car might increase as a result of the collision, and the momentum of another might decrease, but this total momentum of the system will stay the same. A second scenario where momentum is conserved is objects pushing away from each other. You can probably visualize that if two people on an ice rink were to push away from each other, they would slide in opposite directions across the rink. But since they were initially at rest, we'll call this an initial momentum of 0, they would have to have the same momentum going in opposite directions for it to add up to 0. We'll do some practice with conserving momentum. So you have a mass of 80 kilograms, are standing in the middle of a skating rink, holding a 5-kilogram bowling ball. If you throw the bowling ball at 10 meters per second to the right, what are the magnitude and direction of your resulting velocity? So first of all, let's look at the initial momentum in this situation. Initial momentum is 0 because you're at rest holding this bowling ball. You also know that the final momentum will equal the initial momentum. Therefore, the final momentum will also equal 0. So we know the final momentum. That's going to equal m, we'll call this my vy for u, plus m of the ball and v of the ball. So now let's plug in our numbers. 0 equals, your mass is 80 kilograms, your velocity is what we're solving for. The mass of the ball is 5 kilograms, and the velocity we'll call positive 10 because it's moving to the right. Now we can simplify, so 0 equals 80 times your final velocity plus 50. We can subtract 50 over to this other side. Now we get negative 50 equals 80 times your velocity. Divide both sides by 80, and we get that your final velocity is negative 0.6 meters per second, or 0.6 meters per second to the left. Number 2. An 85 kilogram fisherman jumps from a dock into a 135 kilogram rowboat which is at rest. If the velocity of the fisherman is 4.3 meters per second to the east as he jumps, what is the final velocity of the fisherman and the boat? So we can say that the initial momentum of the fisherman plus the initial momentum of the boat will equal the final momentum of the fisherman and the boat together. So let's look at the fisherman first. So we know he's 85 kilograms and moving at 4.3 meters per second. We know that the boat is 135 kilograms, but it's not moving, so it has no initial velocity or momentum. Now when we combine them, we get that the total mass will be 85 plus 135, and the final velocity is what we're solving for. Now we can simplify this a little bit. 85 times 4.3 equals 220 times the final velocity. We'll divide both sides by 220, and we get that the final velocity of the boat and the fisherman equals 1.7 meters per second to the east. Number 3. Train 1 moves towards Train 2, which is twice as massive as Train 1 and begins at rest. After their impact, the trains stick together and move with what fraction of Train 1's initial velocity? Okay, so again we know that momentum is going to be conserved. We also know the initial momenta of both objects. So we'll write that as 1 plus 2 equals p of 1 and 2. So the initial momentum of 1 will be m times v. The initial momentum of 2 is 2m times, and it doesn't have any velocity, so we'll call that 0. And then the final momentum will be the mass of both trains stuck together. So that would be 3m because it's 1 plus 2. And then we're solving for this final velocity. So now we can simplify. This goes away because of the 0. So now we get mv equals 3m times v final. We can get rid of the m's because they're the same on both sides, and divide by 3 to get that the final velocity equals initial velocity over 3. So it's 1/3 of the train's initial velocity.